And when we simplify them, we are going to look for any factors that are perfect squares. And then we're going to simplify them. Okay, before we do that, the last example from 10.1 that we did had an exponent that was greater than a 2. So it wasn't a square root. And so I want to take a look at what do perfect square exponents look like. So we'll have to do a few. It's pretty quick to catch on. So if I had x cubed and this whole thing is squared, I would get, remember we multiply the exponents, so we get x to the 6th. So what that means is the square root of x to the 6th is the principal square root of x cubed. Okay. Now, another thing that we are going to assume from here on is that our variables are positive. And we're going to assume that our variables are positive. So what that means is that we can drop the square root signs. All right. So let's go ahead and talk about, so when you take the square root of a variable with an even exponent, you cut that exponent in 2. And we'll get some examples here. So first thing we're going to talk about with simplifying radical expressions is the product rule for radicals. And if the nth root of a product of 2 numbers is equal to the product of their nth roots, and this is an important product or important property, if the square root of a and the square root of b are real numbers, then the square root of a times the square root of b is the square root of a times b. Now, this is not true for addition, okay, but it is true for multiplication and division. So just combining these, when I look at the square root of 5 times the square root of 3, well, by the product rule for radicals, it's the square root of 5 times 3, or the square root of 15. We can look at number 2. The square root of 7 times the square root of x, well, that would be the square root of 7 times x. And we can't simplify that any further. So we would just say it is the square root of 7x. For number 3, the square root of 5x times the square root of 2y is the square root of 5x times 2y, which equals the square root of 10xy. All right, so we can do that for division and multiplication. We cannot do that for addition or subtraction. So we look at this product property for radicals because we're going to go in the opposite direction when we simplify a radical. And for simplifying radical expressions, when a radical expression is written in simplified form, each of these following is true. So you could also say that each of these following have to be satisfied to know that you are done. The first one, each factor in the radicand is to a power that is less than the index of the radical. Okay, what is the index of the radical? Well, when we look at a radical, this is a square root, but we would say that this is equal to the second square root, because you can have cube roots, you can have fourth roots, you can have fifth roots. Excuse me, but we look at the square root. This little number is the index. We do not write it for a square root. So when you do not see that number in that little elbow of the radical, okay, we know that the index is a 2. So this first property states that each factor in the radicand, which is your answer, or it's underneath the square root sign, sorry, it's underneath that square root sign or the radical sign, has a power less than the index. All right, the second thing that has to be satisfied is the radicand, the number underneath the radical sign contains no fractions or negative numbers. So we have to make sure that we take care of any fractions and any negative numbers. The third thing we have to satisfy, no radical appears in the denominator of a fraction. So that's a process we'll talk about calling rationalizing the denominator. And then the fourth thing that we have to satisfy, there are no perfect square factors under the radical sign. Okay, so it sounds like a lot, but it actually goes pretty quick. And we'll go through this process right now. I want to simplify the square root of 12. So when I look at the square root of 12, I have to make sure that every factor has a power less than 2, okay, because it's square root. I don't see any powers yet, okay. There are no fractions or negative numbers. That's the second thing we have to satisfy. There are no radicals in the denominator. We don't have any denominators. And the last one is there are no perfect square factors under the radical sign. So, well, I know with 12, when we look at perfect squares, I can list them across the top, 1, 4, 9. Because each of these numbers, the reason we can't have these as factors is each of these numbers has a nice rational perfect square. That perfect square principle, square root. So when I look at 12, 4 is a factor of 12. So I'm going to simplify this. And how I'm going to rewrite this, I know that, and we'll reduce our steps as we go along, but I know this is 3 times 4. 3 times 4 is 12. So I'm going to make 2 buckets. The first bucket, radical, is for my perfect square factor. The second bucket, second square root sign, is for my non-perfect square factors. Now, and this is because of that product property for radicals, I can take the square root of 4. It is a 2. I cannot take the square root of 3, so I leave it alone. This is my answer. So that is it in its simplest form. Is we, instead of writing the square root of 12, we write 2 times the square root of 3. Let's try with number 2. All right, with number 2, I have the square root of 50. Well, when I look at the factors, the perfect squares, right? Because I can't have any perfect square factors because I can simplify them. And I look at the square root of 50, and I'm going to make my 2 buckets. Because I know that 25 is a factor of 50, and it has a perfect square. It is a perfect square. And I know the 2 remains. Now I can simplify. The square root of 25 is 5, and I get 5 square roots of 2. All right, let's take a look at a few more. Any questions? Okay, well, now we have the square root of x cubed. Now remember that we are stating that x is always positive now, or it's always non-negative. So we don't have to worry about the absolute values at this time. But when I look at the square root of x squared, I know that I do have a factor. In fact, x squared is a perfect square. And I have to get, the index would be a 2 because it's a square root. The exponent's a 3, so I have to decrease that exponent. Now, if I have 2 factors of x that are a perfect square, I have 1 that isn't. Now notice that x squared times x does give me my x cubed back if I need it. And to simplify this, I'm going to have x times the square root of x. Now, when you're doing your homework in My Math Lab, section 10.1 will still need the absolute value signs. But when you get to 10.3, we no longer need the absolute value signs. All right, number 4. So with number 4, again, make the 2, I always call them buckets, but the 2 radical signs. All of your perfect square factors will go in the first bucket, and what is left or remains will go in the second bucket. So as an example with 18, I know that 9 is a perfect square. So I'm going to put that factor in the first radical. And 9 times 2 is 18, so I'm going to have to put the 2 in the second one, right? Because 2 is not a perfect square. For x cubed, well, x cubed is not a perfect square, but x squared is. And I have 1x that remains. I can take the square root of 9x squared. It would be 3x. And then I would bring along the square root of 2x. And that would be my answer. So with all of these, it is simplifying square roots. Please let me know if you would like any additional examples. Any questions right now? Okay. Well, let's take a look at a few additional formulas. Distance and midpoint. Now the distance formula is perfect for this section because the distance between 2 points, x1, y1, and x2, y2, is given by d is equal to the square root of, and then inside parentheses we do x2 minus x1 quantity squared plus y2 minus y1 quantity squared. All right, so this is a formula we're going to find, and it will be the distance between any 2 points in the xy plane. So I just want to show you with a little diagram. I'm going to go ahead and just try to draw a nice straight here we go, coordinate system here. And we go by ones. All right, and more. So if I were to look at these 2 points, negative 5, 8 would be up here. That's my point, negative 5, 8. Down to negative 2, negative 2, 2. So here's this point, and or these 2 points, and we're going to have this distance here. Now distance, we could also say it's the length of a line segment. Okay, but it's the distance between the 2 points. So with that distance between the 2 points, we would have this formula. And how we're going to use it, we're going to let this first point be our x1, y1, and the second point will be our x2, y2. And we'll just fill in the formula. The distance is equal to all of it, it's all under 1 square root. All right, x2, well, x2 is a negative 2, minus x1, which is a negative 5. And then we're going to square it, plus y2, which is a 2, minus y1, which is an 8, quantity squared. All right, and then we simplify. So with this first one, again, we bring along that square root. Negative 2 minus a negative 5 is negative 2 plus 5, or 3. 3 squared is 9, plus. All right, 2 minus 8 is a negative 6, but negative 6 squared is 36. So our distance is equal to the square root of 45. But similar to when we get an answer with fractions, we have to see if it's in simplest form. And we take out any factors that the numerator and denominator have in common, right? We simplify it. Well, we have to simplify these radicals as well. So instead of looking for a common denominator, we look for a perfect square factor, and we have one. 9 is a factor of 45, and 5 is left over. So we're going to simplify the 9, the square root of 9, and it'll be a 3 times the square root of 5. So the distance is equal to 3 times the square root of 5. Let's take a look at another example. Any questions? Great. So here we have the distance between the points 7, -3 and 5, 11. Now again, we're going to let the first point be our x1, y1. And the second point, 5, 11, will be our x2, y2. I'm going to start by writing down the formula. So we have something to reference as we fill in all of our variables. Distance is equal to the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. Right, we'll fill in what we know. And we know that again, the first point, 7, -3, is my x1, y1. And the second point, 5, 11, is my x2, y2. So x2 is 5 minus x1 is 7 squared plus y2 is 11 minus y1 minus a -3. And then I'm going to square it. So for the first point, 5 minus 7 is a -2. -2 squared is +4. And for the second set of terms, 11 minus a -3 is 14. And 14 squared is 196. Right? So we get the distance is equal to the square root of 200. Okay, well, look for any perfect square factors. I see one right away. It's 100. And then I would have a 2 in the second radical. So the distance between the 2 points would be the square root of 100, or 10 times the square root of 2. And that would be the distance between the points 7, -3, and 5, 11. So the last thing that we're going to talk about, first, are there any questions? The last thing we're going to talk about is midpoint. Now with midpoint, what you are doing is given 2 points on the coordinate system, the XY plane, we're going to find the 1 point. There's exactly 1 point that is the same distance from the 2, equal distance from each of the points. And it's called the midpoint. And the midpoint formula of the line segment whose endpoints are x1, y1, and x2, y2 is the point with coordinates x1 plus x2 divided by 2. And your new y coordinate will be y1 plus y2 divided by 2. All right, so I'm going to draw in a coordinate system. And I want to take a look at this. I'm actually going to take my time and draw this really, really nice. And I want to make sure that I have all right. That's actually all I need. So if we were to plot these points in, I would again have a -5, 8. So we'll be right up here. And my second point is -2, 2. All right, and here I have my ruler. This is my line segment. You could also say that represents the total distance. What the midpoint does is it finds the coordinate of the point that is equal distant between these two. Equal distance. So if I were to look at that, if I were to look at those two, I would say it's, roughly the point -4.5. That would be my guess. My guess here is -4.5. We'll see if that's right, okay? But it's not about guessing, right? We want to find the exact point. There's one point that's the exact distance between the two, and we want to find it. So this point, -5.8, that's going to be my x1, y1. And the second point, -2.2, will be my x2, y2. So the midpoint of these 2 points will be equal to x1 plus x2 divided by 2. And then the second y coordinate, because it's a midpoint, so it has to have an x coordinate and a y coordinate, will be 8. That's our y1 plus our y2, 2 divided by 2. And then just simplify each of those fractions. The midpoint between these 2 points so that is going to be -7/2, or -7/2, -3.5. That was close. And 10/2, which is 5. And this would be our final answer for the midpoint. So my guess was close. I was off on my x term, but the graph wasn't perfect. And we did find it using the formula. Let's do one more. Find the midpoint of the segment that joins points 7, -3, and 5, 11. All right, so without even graphing, we can go ahead and put this into the formula. The midpoint, we add our x terms and divide by 2. Notice that that's the average of the 2 x terms. Okay? Adding 2 numbers, divide by 2 is the average. And for the y, we're going to do -3 plus 11 and dividing by 2. So it gives me a point, it gives me a new x and a new y that is the point that is equidistant from both of the 2 points mentioned. So the first, our x coordinate, is 7 plus 5 is 12, divided by 2 is 6. And the second coordinate, -3 plus 11 divided by 2, well, -3 plus 11 is 8, divided by 2 is 4. And that would be our midpoint. I believe that's the end of our time together.